spectroscopy methodologies, there was really difficult to make a choice because, as you know, there is a plethora of methodologies with pros and cons for various applications. So I decided to follow one leitmotif, which is a specific type of molecular device, which is photosensitizers, which are very useful for presenting methodologies with time resolution in the range of the nano to micro to milliseconds. So I will not touch on ultra-fast spectroscopies. We've heard something about this methodology in the past days. Well, yesterday and today not so much. So please forgive my my choice. It's dictated also by the fact that I'm not really an expert in that field. So photosensitizers. We talk about photosensitization. It is something that is exploited as a methodology to treat microbial infections or cancers. And it relies on the fact that some molecules which are inert in the dark become photoactive, become active when photoactivated by normally visible or near infrared light, and generate reactive oxygen species through two possible pathways. One is the photosensitization of singlet molecular oxygen, and the other is direct reaction through radicals. Essentially, it's a very nice method because it relies on molecules that are versatile in their behavior, in the sense that they can be exploited also as fluorophores. And here you see an example of hypericin. It will be one of the tools we will touch repeatedly during the talk. Sorry, you can see probably not so well. I can see it much better here. This molecule binds to the membrane in the bacterial wall, and if you shine light, it generates reactive oxygen species, and it pinches holes in the membrane. It permeabilizes it and kills the bacteria. It's very effective. What's interesting is that it's a very short-range action. Oxygen decays within microseconds, so unless the target is real close, the photooxidation reaction doesn't occur. So if you were to have a photosensitizer here in the middle of nowhere, it would do nothing to your bacteria. And whereas if you bind it to the bacterial wall, it will be effective. So there is a lot of things you can do also with spectroscopy and, as you can see, with super resolution microscopy. This is a simplified Jablonski diagram. You all know about it, surely. You may remember that we schematize energy levels by bars. So this is electronic energy levels. The thick bars here is the vibrational ground state for each electronic energy level, and the thin bars are vibrational sublevels. Arrows indicate transition between states. And what we will do is we'll touch methodologies that are able to have access to fluorescence emission, phosphorescence emission, triplet to triplet absorption, ground state bleaching, and if we manage, probably not because there is not enough time, we might touch also on photoacoustics, which is a method that is sensitive to the broken arrow, the brown broken arrow, which are non-radiative relaxations. Again, here is hypericin. In these molecules, everything starts with absorption of a photon. Here is a famous picture depicting different colored fluorescent proteins. Here the physical observable is photon absorption, but we normally call it absorbance in a spectrophotometer, but eventually it's photon absorption. And what we watch is S1 or SN formation. So by shining a photon, it can be absorbed by a molecule only if it meets the Planck's equation selection rule, which tells you that unless the photon has the right energy, according to this equation, there's no transition. However, keep in mind that this selection rule doesn't tell you the probability. It only tells you that it can or cannot occur. To dig into that, you need to access another parameter, which is the transition dipole moment. We will not touch that, but you all know that in the absorption definition in the Beer-Lambert law, there is this term which is called the extinction coefficient, which is dependent on the wavelength, and essentially it reflects the probability of transition at each wavelength. Here is the other leitmotif, which is TSPP. I will not say the full name. It takes 20 minutes to say. But it's important to show this picture here because you can see that you have two different transition dipole moments which are orthogonal to each other, and they're apparent also in the absorption spectrum, which is down here. This is the transition with QX and QY, and the two bands correspond to the vibrational bands 0, 0, 0, 1. The big intense band is called the Soré band and corresponds to the transition from S0 to S2. All methodologies that we will touch on can be described as relaxation methods. Essentially, you come with a perturbation, which is very short in comparison to the events you want to follow, and then you watch the system go back after removal of the perturbation. So it's really important that the perturbation is short, otherwise you mess up with your kinetics, and you measure a mixture of the two. In some cases, this is possible, but in some cases, it's not. Therefore, in the data analysis, we will be forced to use the convolution methodologies. And we see the first method right away. So the same picture we saw before is now shown as fluorescence emission. You see the colors are different. This one was blue, and now it's red. It's fluorescence emission from a red-emitting fluorescent protein. In this case, we watch S1 relaxation. And the physical observable, again, is fluorescence photon emission. Fluorescence is very beautiful. David Jameson used to say that one of the reasons why he's using fluorescence is that it's pretty, and I think he's absolutely right. You can tell how pretty it is from the face of these kids in a popular science event. You show them fluorescence emission, they're like, blown away. There are a number of things that are fluorescent in your everyday life. So if you're interested, you can ask me afterwards. Let's go back to the Jablonski diagram. Well, if we shine light, we end up generating this vibrationally relaxed S1 state. And from there, everything happens, because we generate that state very quickly. The decay is accompanied by fluorescence emission, but also by heat release through internal conversion to S0 or intersystem crossing to T1. If you shine continuous light, like in this drawing, what you see is that essentially you see continuous light emission. Like if I like to bring toys with me, so I'll show you one. So this is one of the slides people use to align microscopes. That's fluorescence emission. If I shine CW light, you still see the fluorescence emission. But when I shine the light off, fluorescence is gone. It's an event which takes very little time. If you remove the perturbation, the event is gone very quickly. So if we want to measure and characterize excited state relaxation, you want to measure the rate. And to measure the rates, no way you can use steady state methodologies. You need to use time resolved, which means that you need to come with a perturbation, generate your excited state, and then watch relaxation, so that in this way the pulse that you shine generates a decay, and normally the decay looks like an exponential decay. Looks like an exponential, it may not be an exponential decay. It looks like a straight line because here you see it's plotted in a semi-log drawing. Rate equations, very important. This is just an example. The probability of the decay of this rate, of this state, is proportional to the concentration of the state itself through a proportionality factor, which is the sum of the three rates which appear here. It's a very easy differential equation. You can solve it immediately to get an exponential decay where this lifetime is 1 over the sum of the rate. It's important to make a further how can I say, reflection on this meaning, because when you have an exponential decay, this is the proportional to the concentration at time 0, so at the end of your perturbation. But don't forget that the lifetime has the following meaning, is the time that corresponds to the time where the signal became 1 over E, the initial signal. And then when you plot it in a semi-log plot, the slope is -1 over tau. It may be very useful. However, with no modern computer, has no real need to be done. But if you want to make sure that the system is mono-exponential, plot it like this, because it will look immediately a straight line. If it's not, it requires that you get into that more in detail. Pulse fluorometry is normally used to measure the decay. Ideally, one comes with the delta pulse, which is just in the book of the tails. And then you measure the response, and that might be an exponential or a sum of exponential. You never see something like this in your lab, unless you have a very short femtosecond pulse and a very long-lived fluorescence emission. In general, what you have is something like this. The excitation has a finite width in time, and that messes up with your decay, which doesn't look like a pure exponential any longer, but has a rise and a decay. But the rise is essentially associated with the fact that the perturbation you come with is large in comparison to the decay. And the result is that you measure the convolution of the excitation and the real decay. Real decay, which is an exponential. You can measure this very quickly with a scattering material. And that reflects not only the laser, keep in mind, but also the response of your detection system. And in many cases, it's not the laser, the limiting system, but your detection system. How does the instrument look like? Looks like any fluorometer. You have a laser, you shine light on your sample, and at right angle you collect the fluorescence emission through a monochromator and a photomultiplier. Photomultiplier looks like this. It's a very old-fashioned picture. Nowadays they are much more compact and small and fast. Typical specs, resolution is in the 50 picoseconds range, excitation can be in the picoseconds. If you have a Thai sapphire laser, you can come with a femtosecond excitation. Repetition rate of the pulses can be up to 80 megahertz, but be aware that if you are shining very fast, you cannot measure long-lived intermediate, because 12 nanoseconds is very short. And I will show you an example where you need at least 100 nanoseconds. Here is an example. You have a variety of small size solid-state laser available today, emitting in the picoseconds. I have several in the lab emitting 50 picosecond pulses, very short. In some cases, you might want to go for LEDs. They are broader, but they have the advantage of being cheaper, so you can buy more for the same budget. Nowadays, the vast majority of methodologies rely on time-correlated single photon counting detection. In these experiments, essentially, we exploit the Poisson statistics, and we shine sequential light pulses separated by some amount, and we collect at most 1 photon after each pulse. And we tag the photon not with the fact that it's a photon, but with the arrival time, which means the time difference between the excitation pulse and the arrival time of the fluorescence photon. In many instruments, be aware that they work the reverse. Instead of measuring this distance, they measure this distance, so from the next pulse. This is because this way there is no dead time, essentially. Otherwise, you have to wait for the system to rearm, and that sort of decreases the efficiency of the detection system. Since you pick random, photons accumulate where the probability of emitting is higher, which means here where the end of the laser pulse is, essentially. And then if you look at the histogram, it looks like the decay you would have in a continuous acquisition. However, this is statistically much more convenient. A signal would look like this, and this is the example I mentioned before. This is TSPP, and the lifetime is 10 nanoseconds, which means if you want to follow the full time course, you need 100 nanoseconds, like here. So forget about using 12 nanosecond separation at 80 megahertz. You will mess up your kinetics. Advantages. So TCSPC has a very high dynamic range, at least 4 orders of magnitude, but very easily can be 5. Has another advantage. The background is virtually 0. In a standard setup like the one I have, you count a few photons per second for the full time range. And in fact, after the complete acquisition, you see you count 1, 2 photons in the background, in the channels. And there's no background that offsets your sample, essentially. Plus, there is a major advantage, which is the statistical meaning of the data we acquire. We know from Poisson statistics that the standard deviation is the square root of the number of photon counts. So you count photons, and you get for the same number also the sigma, not only the value of the signal. And that's very important because that allows you to run a statistical test to judge the quality of fit. So you can use the chi-square directly. Analysis. You can go through the convolution because in the short time scale, even if the lifetime is long, you have distortion in the signal. So you want to deconvolute. And the blue curve is the result of the reconvolution of the impulse response function here, the green. That's the laser pulse, essentially. With the model, it's a single exponential decay. You see that the lifetime is 9.92. The error bar is in the 50 picoseconds. Let me make a note. This is not the numerical error bar. If you were to use the numerical error bar, it would be much smaller, maybe 10 times smaller. But the numerical error bar has no meaning. If you want to know the error bar, do the experiment many times. That's the only way you can estimate the error bar in your system. Repeat it. But you can also make a tail fit. So forget about the convolution, that's simpler. Of course, what you do is you miss this part. You cannot fit that part using a simple exponential decay. But if you look at the numbers, they are identical, essentially. So there's no difference. Except that if you have a short-lived intermediate, remember, go for the convolution. Normally, these programs are provided by the company that sells you the equipment. I should wear the glasses because I don't know how long I've talked. Yeah, 19. Artifacts. You know that all methodologies have artifacts. And the important thing is to be aware of them. That's the signal we saw before. And that's the same sample, same cuvette, detected in the same setup in my lab, moving a mirror and going to an old PMT. So the difference, as you can see, is incredible. It looks like it's a different sample. In fact, it's the same identical sample. And if you fit this decay with the convolution, you get the same lifetime that you get with the left signal. Except that here you have a very high background. You see, even for the IRF, you have a background which is in the order of a few tens. Whereas here, you have 1 or 2. So it's orders of magnitude worse. In addition, fluorescence emission is weak. And so you have to count photons for longer times. That means the background keeps going up and up and up and becomes even 300 here or 400. Again, it's more cosmetics than real issues. But keep in mind that when you see something like this, it's not a straight line. It may not be a multiple exponential. It may be simply a background effect. talking about artifacts, spectral sensitivity is another issue. Photomultipliers have a sensitivity curve, like here. If you go to the red, they are normally very poorly sensitive. And also if you go to the far UV, but that's less interesting for fluorescence emission. So if you measure photons down here, as we do, the sensitivity is very low. Of course, you can buy photomultipliers with red enhanced sensitivity, but that was standard photocathodes. What's the consequence of this? Well, you see two spectra here. There is this one, the dark red one. That's the uncorrected spectrum measured with the system I showed you before. And it looks like it has two emission bands. It's two vibrational transitions. They look nice, but if you measure with a corrected instrument, corrected for the PMT sensitivity, this is what you get. It's clear indication that here your PMT is not sensitive. So you have to correct for that. And it's very easy to calibrate your system if the producer did not provide you a calibration curve. Just go for a calibrated instrument, measure a spectrum, go to your instrument, measure a spectrum, take the ratio, and that's the correction, like done here. It may be useful to collect not simply the emission at a single wavelength. Keep in mind that any wavelength you pick in the emission should be pretty much the same lifetime. But in some cases, this is not true. And to make sure that you're not collecting something that is changing behind after excitation in time, you should collect time-resolved emission spectra. That means you collect the traces, the kinetics we saw before, at a number of emission wavelengths. Here, for instance, it is scanned between 500 and something and 800 and something. You see that they change because you have stronger emission where the probability of emission is higher, weaker emission where the probability is lower. And if you correct your spectrum for the spectral sensitivity, this is what you get. You have a decay, and if you make a contour plot, like in the plot to the right, if you cut a slice at a fixed time, you see the emission spectrum we saw before. But if you cut a slice in the other direction, so you fix the wavelength and look at the time dependence, you can see the kinetics of the decay, as we saw before. You can do that for every wavelength. And if the system changes after photoexcitation because of a phototransformation, you may be able to see not this very nice single decays plots, but you may see bands appear somewhere here. As we saw, I believe, this morning in one of the presentations where the absorbance was changing. This is fluorescence, but it's pretty much the same thing. In summary, let's go to quantitative estimates. We measure lifetime, and we get the rate for the lifetime, from the lifetime, 1/tau. So if you know the fluorescence yield, a very important number, which is the ratio between the number of emitted photons and the number of absorbed photons, then you can exploit this equation to retrieve the value of the radiative rate constant. Keep in mind that the lifetime and the rate, 1 over the lifetime, is not the radiative decay rate. It's not KSR. It's the sum of these three, because you are measuring disappearance of this state. And the rate of disappearance is the sum of the rate. It's not a single rate. So if you want to go to one of the rates, you have to make some mathematics, like we do now, and retrieve that by measuring independently some other parameters, like the quantum yield. I will not touch the quantum yield. So this is an easy experiment I've done at home. This is a laser pointer. Shine the laser pointer off, and you see still light emission. It's a very common phenomenon. It's called phosphorescence. It looks like fluorescence, except that it takes forever to turn off. It's quite useful because, like here, for instance, I took this picture on the flight to here. And you can see the stripes, they are glowing. And there are security stripes that tell you where the exit is if it becomes dark and you have to exit through an emergency door. No, there's no, normally the green signs like that one, let's see if it's phosphorescent. No, it's not phosphorescent. Many times they are phosphorescent. Look at them, but it's not the right color probably because it's green and that's green, so it reflects. But in many cases, those signs are phosphorescent. So if it gets dark, they still emit for a while. What's phosphorescence? Well, we were watching at this guy decaying, fluorescence is emitted, some heat is released, we will get to that later, but we also have intersystem crossing as one of the possible processes. T1 can be populated in violation of the spin selection rule, because in principle, changes cannot occur if the total spin changes. Delta S has to be 0, and here it's going to be 1, because we move from singlet state, S equal to 0, to a triplet state, S equal to 1. It has 3 orientations. So this guy is a sort of a kinetic trap, because it takes forever to go back to S0. It's unstable. Keep in mind, another note, we are studying relaxation of states which are far off the thermodynamic equilibrium. Far off means orders of magnitude. So they will be eager to go back. They will be pushed by the Boltzmann statistics to go back. However, here there is a barrier to overcome, which is due to the selection rule. But the barrier is not infinity, so it will be overcome at some point. And this is what happens. You have phosphorescence emission or heat radiation emission, and you may have photosensitization of singlet oxygen. We'll get to that later. A major difference in the emission is the fact that the time it takes to emit photons here is much longer. It's not nanoseconds, it becomes microseconds or milliseconds, or for a solid material, even seconds or minutes in some cases. So the setup looks like the fluorometer. In fact, it's the same setup, except that the laser has to be used at low repetition rate because the emission is very slow, so you cannot come at megahertz. You have to come at kilohertz because the time it takes is 10, 20, 100 microseconds in some cases. And in addition, you need to have a red sensitive photomultiplier because phosphorescence is emitted to the red of fluorescence, always. So keep in mind another rule of thumb. Absorption, fluorescence is to the right of absorption, and phosphorescence is to the right of fluorescence because you have decreasing energy each step you take towards S0. The detection, however, is very different. Since we go very low repetition rate in this kind of experiments, we collect all photons, not a single photon after each pulse. And the way we do that is we shine a pulse and we exploit the trigger pulse that tells the laser to shine light on a sample to start a sweep where there is a series of gating time and photons are counted in each gate and they are binned with the width of the gate. Of course, the resolution is low. It cannot go 50 picoseconds in this case. It will be in the 10, 20 nanoseconds range. But we don't care because the decay takes microseconds to occur. So who cares about going to 50 picoseconds? And eventually you end up with an histogram, just like in TCS-PC. And this methodology is called multi-channel scaling, MCS. Here is an example with hypericin. Oh, this is for Sofia. This is hypericin in myoglobin. Instead of the heme, here you have hypericin. It becomes phosphorescent, as you can see. It emits at 1100 nanometers. plus you generate singlet oxygen. So you see also phosphorescence from singlet oxygen here. It is further to the red because it has lower energy in comparison to the triplet state. The thing you see is that you have formation and decay, which is triplet state decays and form the singlet oxygen, and then the singlet oxygen decays. So it's a double step event. Again, for triplets, we have the same rate equation we had for the singlet. It will be a decay through different channels, and the overall rate will be the sum of the rates. It will be phosphorescence and intersystem crossing. However, unlike what we saw for fluorescence emission when S1 decays, here we have an additional term for the probability of emission, which is dependent on the concentration of oxygen. So you have a diffusional rate constant here times the concentration of molecular oxygen. It tells you that this rate, overall rate, will be oxygen dependent, very oxygen dependent. We'll see an example shortly. We will see the example using nanosecond flash photolysis. That's the technique I like the best. Many of you, maybe, but this is a picture taken in the lab by a student of ours who was visiting us for a year. And she was a semi-professional photographer, and I always envied her for being able to take such pictures. I tried it many times with my reflex, no way. It's very difficult. You know that the methodology actually was developed in the 40s for totally different reasons. Norrish and Porter were awarded the Nobel Prize in '57, if I'm not mistaken. 57 or 65, well, those years. Because they developed in '49 a methodology to study radical reaction and triplet state decays in the solid state and in the gas phase. And they were using at the time not lasers, because the laser came afterwards. They were using flash lamps and techniques that were at the moment available due to military applications. They got the Nobel Prize for that, together with Manfred Eigen, who developed the methodologies that we call T-jump, for instance, and others. So transient absorption. When we pump the system with a nanosecond pulse, we generate S1 and then it decays. But when we generate S1, we have one effect. We deplete the ground state. So there is one immediate effect, ground state bleaching. There is always, whenever you shine light, ground state bleaching, which is a negative absorbance change. It can be large, small, depending on how strong your excitation is, but it will always be there. But in these molecules, we end up generating triplet state after passing through the singlet S1. And when you are in the T state, now a number of transitions become available. You would not be able to go from S0 to T1 or from S0 to T2, because that would violate the spin selection rule. But from T1, you can go to T2 or T3. So new absorption becomes available. And normally, again, the absorption TT is always to the right, to the low energy side of the absorption between the S state, because they are closer in energy. Again, the kinetics of triplet decay will be modulated by the presence of molecular oxygen. How does the system looks like? Well, there is a laser, of course. Nowadays, lasers look pretty much all the same. Nanosecond laser, you have a YAG laser, harmonic generators, and you may pump an OPO. OPO allows you to tune the emission between anywhere in the UV and anywhere in the infrared with more or less energy. And then you have a detection line. You may have several methodologies. I'm showing you one because it's flexible. But keep in mind that there is another one, which I will comment on later, which is similar but substantially different. So you have a xenon lamp. Xenon lamps are important to be used. Don't use any other type of lamps because they are too weak. Plus, they have a major advantage, xenon lamps. They emit through an arc. They ionize the gas. And what happens is that the arc is tiny. So it's very efficient decoupling with the monochromator. If you have to buy a lamp yourself, prefer 75 watts. That's by far the best lamp. It's the smallest arc you can get. My personal opinion as a user. So you have a filter here, maybe a polarizer, and very important, a shutter. You see that the white light doesn't hit the sample all the time. And then you have optics for conditioning the beam, a monochromator, and it might be a spectrograph as well. In this setup is a spectrograph. And depending on how you use it, you may go to a CCD for spectral acquisition or to a single wavelength detector like a PMT or a photodiode. In some cases, photodiodes are advisable. Typical specs are that excitation pulses are in the 5 nanosecond range with millijoule energies. So it's tough, it's megawatts. We are not talking about low power. Time resolution is in the order of 10 nanoseconds. With my setup, typical resolution is 8 or 9, depending on the sample. Excitation range can be determined by the laser, and detection is determined by the sensitivity of detection setup. So the way it works is something like this. You open the detection bin right before the laser comes. And that's because if you shine these few watts of white light on your sample, you may not be happy. So you protect the sample, essentially. And then you repeatedly shine the laser to accumulate signals and reduce the noise. Here is a picture showing some details. Here is a pump laser, harmonic separator, OPO, and here you have the xenon lamp. Here is a filter that was taken out, a lens, a shutter, a filter. This is the sample holder for temperature control, optics, spectrograph input with the filter in front of it. Very essential. Some samples don't like white light. So if you shine white light, they are dead, like photoreceptors, to name one. So you should use 2 monochromators. It's more complicated because you should exit here with a monochromator, recollimate the beam, refocus, recollimate the beam, refocus. So every step you miss some photons. That's the only thing you can do. But it works. I have that as well in the lab. It's stuck. Sorry. Yeah, it's gone. So since we shutter, the signal is not always there. It's there only when the shutter is open. And it looks like this. So 0 light on your detector, open the shutter, light on the detector. You see there is some drift here you have to take into account. But normally it's not important because what you do is you're shining your laser after some time so that you're in the middle where the signal is flat. And that's how the signal would look like. That's your baseline, the signal without the laser, and that's your signal, the signal with the laser. And from those 2 signals, you can very easily calculate the delta A at that wavelength by taking the ratio B over I and taking the log of this ratio. You see the signal can be very nice. This is very big. It's an unusually big signal, but that's for showing. Life is not always so good. Here is the overall time course on a log time scale. You are aware that in biology, signals are extended in time. This is one example, although the biology is very simple. It's a photosensitizer. But you can see that there are kinetics here in the long nanoseconds, well, not so long nanoseconds, in the tens of nanoseconds, and it keeps going here in the microseconds. So it's 4 orders of magnitude. What is this signal for? This is the signal that corresponds to decay of the singlet state to the triplet state. It's this rise. And then decay of the triplet state. It's this decay. The decay has a lifetime of 1.7 microseconds. Keep that number in mind because all triplet states in water equilibrated with air at room temperature live 1.7 microseconds. It may be 1.9, 1.6, but they all live the same because that's a lifetime determined by oxygen concentration. If the lifetime becomes longer, it means it's protected. If the lifetime becomes shorter, it means there's something else. So this method, it's okay. It allows you to follow triplet decay, but also allows you to see triplet formation. And although with the limited time resolution, you see that this number is very similar to the decay of TSPP we saw before. You remember it was 9.8 nanoseconds. It's not identical. And the problem comes from the fact that the laser pulse messes up a little bit the kinetics. So this is an artifact. You know that it's the same process, but you cannot rely on this number. It's there, you know it's there, but you should go for deconvolution if you want to get the proper number. Now that's single wavelength detection. If you use the system with the spectrograph and the CCD, you take a snapshot at fixed times. And the snapshots can be taken like with a gated CCD that allows you to take pictures with exposure times as short as 2 nanoseconds. So you can make very precise and time-resolved acquisitions. The principle is the following. This is the time the laser comes. You collect your reference profile before the laser hits, and then you set the delay at the value which is after the laser pulse, and you collect the time, the wavelength dependence of the intensity. You see they are different, and if you plot them together, you can clearly see that some regions have lower intensity, so here you have absorption, and higher intensity, here you have less absorption, than after the laser pulse, which means something changes in the color. You should measure the background, and my setup is quite old, so the background is very bad. You see it's quite high, but if you buy a new one, it's not as bad. So if you see something like this, they gave you an old detector, like mine. Probably it's mine. Yeah, I wanted to have that. If you correct for the baseline, for the background, and you take the ratio and the log, you get the absorbance change. But now it's different. It's the absorbance change as a function of wavelength at a given delay. Now, if you change the delay, you can follow the time evolution of the absorbance change, of the spectral absorbance change. Keep in mind, this is very useful to identify reaction intermediates that are different in terms of spectroscopic properties. But if you want to measure kinetics, the other methodology is by far the best. Single wavelength provides you with hundreds of thousands of data points for the kinetics. In this case, if you're lucky, you get 100, because it takes a long time to collect these data. This is another way of plotting it. If you select this wavelength, you see the bleaching recovery. And if you select this one, you see the triplet state formation and decay. But if you cut a slice at a given time, you get the absorbance change, as we saw before. If you remove oxygen, you get the cyan curve here. So essentially, you get rid of the quenching term, the one that is dependent on oxygen, and you see that the lifetime becomes much longer. So now you see the extension in time becomes even longer. But that's a very important number, the lifetime of the cyan curve, because that tells you what is the intrinsic lifetime in the absence of quencher. And if you get that, you can calculate by measuring KT the value of KQ. So how efficient the system is in quenching the triplet state. Like in the case of TSPP, in nitrogen saturated, remember it was 1.7 microseconds. Now it becomes 300 microseconds. Very long. And if you use this number in this equation and you measure in air equilibrated solutions, you get KQ, which is 3 × 10⁹, which is the usual number for diffusional quenching. I have 5 minutes. 5 minutes. Okay, so I'll say just a couple of words on time-resolved photoacoustics. I like photoacoustics very much, as some people in the audience know. For historical reasons, my PhD thesis was on that, so my heart is with photoacoustics. It's not very fashionable, but you will see it's very useful. So in this diagram, photoacoustics is sensitive to any of the broken arrows because they're all non-radiative relaxations. The physical quantity we measure, however, is not heat directly. It is pressure changes through a microphone, a piezo microphone. Again, I will not be able to give you many details, but if you're interested, come and ask. I said we don't measure directly Q, but in fact, the molecule releases Q to the solvent. So Q brings with it some delta T through the heat capacity. And delta T brings with it some delta V through the cubic expansion coefficient. But in some cases, molecules change their volume. So they generate the volume change directly without going through the steps in the first line. And both, through the isothermal compressibility, generate pressure changes. And if you have a microphone able to detect the pressure changes, you can measure the pressure change induced by light absorption. The setup is very similar to any other setup we've seen before. We have a pulse laser, usually a nanosecond pulse laser. You monitor the energy of the pulses. You shape the beam with a slit, and then you hit the sample in a cuvette. And the transducer is one of those piezoelectric PZT transducers. You may not be aware, but they are identical to those they use in echography. So you know when they make imaging, they're exactly the same type of transducer. And it's a contact transducer, so you have to attach it, physically attach it to the cuvette. And the pressure wave, when it reaches the transducer, gives you a signal that looks like this. It's resonant signals, and they are damped, so the number of oscillations you get is like 2 or 3 at most. Again, will be very essential. The intensity of the signal can be heuristically described by this equation. It's proportional to the number of absorbed photons, and it's proportional to the heat released, which is alpha times E lambda. Alpha is the fraction of absorbed energy released as heat, plus a volumetric term. To calibrate your system, you normally rely on a molecule that absorbs photons and goes back to S0 very quickly, doing nothing but releasing heat. Think of the molecules you have in your black T-shirt, for instance. They absorb light and heat you when you're in the sun. They do exactly the same. It's the type of molecule that do not go through any photochemistry, any fluorescence, no nothing, just heat release. And using that, alpha becomes 1, so alpha E lambda becomes, as you can see, 1 here. Okay, so that's the equation, no volume change. That's our calibration signal. How do the signals look like? That's the way they look like. This is your calibration curve. That corresponds to the response of your detection system when you have full release of absorbed energy as heat. That's the largest. And as fast as it can be released. So the signal is to the left of your plot. For your sample, you may have some missing energy here that can be due to fluorescence or can be due to time modulation. Time modulation brings about a change in the shape of the signal, like in the sine curve here, and the fact that the heat released is multi-exponential has as a consequence the fact that the signal is distorted in comparison to the instrument transfer function. The black signal is like the pulse in the fluorescence emission, except that since this system is resonant, you have the ringing. Otherwise, you would have the pulse and then the exponential decay. But since they are ringing, they are convoluted. If you want to retrieve the exponential, you have to go through the convolution just like in fluorescence. There's no difference. It's identical. Here is an example with TSPP, and I will finish with this. You see that the convolution affords 3 lifetimes. One is S1 decay. It's very fast, 10 nanoseconds. We've seen that before. T1 decay, 1.9 microseconds. It's the 1.7 I told you before. And then singlet oxygen decay, 3.3 microseconds. So you see, you separated the heat release of each step. And if you're able to do that, you can retrieve information on the energy content of each intermediate and the volume change that accompanies that. If you look at this equation, it's the same equation we had before, but it has been rearranged to expose here the amplitude of the deconvolution analysis. And here you have the heat release, and here the volume change. And you see that if you consider this term, which is temperature dependent, you may have a linear relation. And if you plot this number, and remember this one is the amplitude of each deconvoluted transient exponential decay, I would say, if you plot this number versus this number, you get a straight line where the slope is the volume change and the intercept is the energy content of the species. It's very important to realize that we are talking about energy content of species which have intermediates, very difficult to characterize. Like here, for instance, this is the triplet formation. That's the energy associated with that. And from the slope, you can see that there is also volume change, a negative volume change. I will not describe that into detail. But if you remember, it's a macro cycle with nitrogens, and 2 of them are protonated. So when you excite the system, there is an accumulation of electron density at the nitrogens that grab water molecules, and the overall volume is decreased. When the triplet decays, the electrons go back to their original position. There is no excess of charge, and there is an expansion because the water are released. So it may be complicated, like in this case, that's the energy balance of the molecule. We don't get that into details, but I want to show you that if you plot the equations for the energy content of each of these terms, you can see that, for instance, this one you measure from photoacoustics. This one is known as the triplet yield. This is the singlet oxygen yield. But this one is something that people never know. So the triplet state energy is very difficult in general to see, to determine. The only determination is through phosphorescence emission at cryogenic temperatures. But that might be very different. So again, this is a simple experiment and exposes you a number which is otherwise difficult to retrieve. So it's a simple molecule, but translate that into a more complex system. It can be intermediates in your photocycle for photoreceptors. If you are able to separate the steps, you can calculate the energy content of each of them, something that is otherwise very difficult to get. Plus, you get the lifetime of the relaxation without any need for a chromophore, because the signal comes out for itself. Okay, so this is the end of the arbitrary selection of methods I made. I hope I didn't bore you too much. I'm open for any question now, in the time we have, in the next days, in the next month. You know my email, so just get in touch with me if you need it.